Good afternoon, everyone. I would like to thank everyone that attending this Frame Mobility Research Institute webinar. Also, I would like to thank the IT FAU chapter that help and coordinate with this webinar. It is my pleasure to introduce Dr. Mihalis Golias. That's a professor in the Department of Civil Engineering at the University of Memphis. That he holds the PhD and master degree in transportation from Roadway University and BS Bachelor from Aristotle University of Thessaloniki in Greece. His teaching and research cover the area of maritime and freight transportation in a few physical network and vulnerability, and of course resilience, capital and operational resource allocation, multi-level, multi-criteria decision making, and also Dr. Golias is the Associate Director of the Frame Mobility Research Institute. He's going to present this extremely important work with a case study in Florida with Miss Aline Machado, that she just graduated with a master's degree in transportation from Florida Atlantic University. During her studies, she conducted various research in freight transportation and intelligent transportation systems. She has applied programming and data science to improve the overall transportation network performance. And as a student, she was really active with the different roles, especially leading positions at the Women Transportation Seminar at the Florida Atlantic University student chapter, and also she was involved with the IT at the FAU. Mihalis, the floor is yours.
Thank you, Vangeli. Actually, the floor is Aline's, as she's going to start the presentation, and then halfway through, I'm going to pick up where that's how we decided to go about. So, Aline, the floor is yours.
Thank you. Thank you, Dr. Kaza, for the introduction. And my name is Aline Machado, and I'll start the presentation, and then Dr. Golias will take over. So today we'll present this research project. It was called Identifying Critical and Vulnerable Freight Routes in Roadway Networks. And it's a game theory framework and an application in the state of Florida. This was led by University of Memphis and FAU, and FAU conducted the necessary data collection task. So the next one. This is the outline for this presentation. So basically the introduction, methodology, results, and the conclusions. So the transportation networks are vulnerable to natural disasters such as the collapse of bridges, landslides, tree blocking, failure, flooding, etc. And the infrastructure is also vulnerable to man-made disasters such as dam collapse, flooding because due to impermeabilization of the surface. There are floodings that can be classified as man-made disasters. And in addition, the transportation network are vulnerable to incidents, such as accidents and bad conditions of the infrastructure or poor maintenance. The transportation network in the US is one of the largest and oldest in the world, and making it also vulnerable. There are roads that were built during the colonial era, and the first transcontinental road was built in 1913. Next one. And it is of crucial importance to identify the vulnerable and critical links and routes in the transportation network, and we must also take action to protect and fortify the existing infrastructure against such disaster or incidents. Next one. So addressing network vulnerability of transportation assets in general will minimize impacts of disruption, reduce recovery time, and improve the region's resilience. The benefits of this project comes to the fact that from 1980 to 2011, there has been 133 disasters designated as billion-dollar disasters. And causes of this disaster are caused by humans, for example, bridge collapses due to improper maintenance of the infrastructure, and more commonly, traffic accidents, as we know. With freight network acting as economic pipelines that distribute goods throughout the region, disruptions to the network can have widespread consequences, and the proposed research and its outcomes can support a better understanding of operating and modeling multimodal freight transportation network under extreme conditions. Also improve accuracy of freight fluidity, measurement at the local, regional, and national level, evaluate and improve decision making for optimal freight movements, and also helping evaluate and improve the resilience of freight network. The goal of this project is to develop models and tools to deal with freight network vulnerability and resilience that capture long and medium range, pre and post disruption network conditions, route travel time, what are the impacts on passenger, freight movement, and response and rescue team, and also access prevention to critical infrastructure, facilities, equipment before, during, and after the event. For the literature review, Dr. Golias will take over the presentation.
Great, thanks, Aline. So, network vulnerability, resilience, and a bunch of other terms have been floating around in the literature review. And what it comes down to is trying to identify either links or paths that can be categorized either as critical or vulnerable, at least based on our definitions. So critical links are the ones that are most likely to lose capacity, and then vulnerable are the ones that will experience severe effects if a critical link loses the capacity. So with regards to what are the measures of vulnerability and criticality, most of them are a function of time and then accessibility, shortest paths, flow, either passenger or value if you're talking about commodities. But I think we have in the report a table that's like 5 pages long of the different measures that people have come up with to calculate vulnerability and criticality. So obviously we're not going to list them here. Now, if you go out and you look at the list at the research, the majority of it focuses on links, and then some of it focuses on identifying paths. Most of it is single links. They don't go into the approach of estimating vulnerability for sets of links, so when a combination of links fails. And usually in a network, when you have a disaster like a hurricane or an earthquake, right, not even accidents, those don't happen on single links and then the rest of the network behaves like a typical day. You have it on a sets. And that was actually the goal of the project, is to figure out sets of links, not just individual links. The approaches, pretty much, they're the 2 main categories. They either look at the network as a graph, and they just focus on the topology of the graph, so they disregard demand and supply, or they just focus on the traffic-based analysis. And then there is a combination where they try to create topological-based vulnerability criticality measures that are infused with traffic-based measures. All right. So in this case, we're using the latter. As part of this project, one of our PhD students who's graduating this semester, she developed I believe 9, and we tested it, and 3 of them showed to have good properties, and those 3 combination of topology and demand we're using in this project to identify the links that are critical. With regards to solution approaches, so that focuses more on the demand supply, because whenever you start doing demand supply, you're looking at a game theory framework. So usually a network design problem with either 2 or 3 levels. In this project, we used a 2-level that can be expanded into a 3-level. We'll go more into detail in the next slides. So you can either use optimization and simulation, either individually or in combination. And again, the thing that really needs to stand out from the literature is that the most common approach, the most thing that most people do, is they take a network in Memphis, in Florida, whatever it is, and they start removing links one by one. After they remove a link, they run the network and they see what's the new congestion levels, right? Travel times or vehicle miles traveled, or whatever the measure is. And then that's how they rank links. But again, in this approach that we're using, we acknowledge that links don't fail individually, and we want to see which are the sets of links that are most critical. So this is how the modeling network looks. This is the genetic modeling network of a network design problem, and our problem falls under network design, just like many other problems. So essentially, in the network design problem, you follow a hierarchical formulation in order to capture the interactions between what we call players, right? And the reason why you want a hierarchical framework is because they don't all play at the same time, right? So if you have a roadway network and you have a decision maker, let's say a DOT, an MPO, that wants to do an improvement on a network, right? First, they're going to do the improvement, then an event is going to happen and it's going to reduce capacity of the network, right? So, and then the users of the network are going to see what's the state of the network and try to go from the origin to the destination, right? So it's the network design model tries to capture the fact that the players each take turns in making their move, right? So it's different than a Nash equilibrium where everybody plays at the same time. Now, for certain network design problems, and I'm not sure if you can see my, the mouse. No, this is annotation. My apologies. Give me a second. I'm not used to I'm more used to the Zoom, not the WebEx. I'm trying to find the pen here. Nope. All right, I think this should work. So this player and this player, right, there are certain network design problems where the two players play simultaneously. So the whole first and second level are joined into a Nash equilibrium, usually. In our game, we actually consider that player one and player two will have the same objectives. So essentially, we turned the upper and middle level, if you want to call them that, into a single level by using a minimax problem. And again, I'm going into a little bit of detail for those who deal with the optimization side of the network design, but it's not important for what is the goal of the presentation today, which is to show the tools have been developed, a couple of examples of results, and to just showcase the capabilities of what you can do with the final product of this project. So let me see if I can, I need to close annotation. There we go. So the performance measures that we use, obviously, criticality, probability of attack, vulnerability, what's the increase in VHT and VMT. And then, again, we did sets of links, not individual links. Individual links is very simple to do. You can do it within an hour for a network like the one that we used, or maybe a day, depending on how congested the network is. And then the other thing that we did is we used the individual links based on their criticality, vulnerability to create paths, right? Because at the end of the day, when you're doing planning, especially for freight, but for passengers as well, you're interested in paths, right? Which are the ones that are going to be more critical? Which are the ones that I need to pay more attention to? So again, for those who do optimization and are on this network, we developed 3 heuristics. The first one is what we call a very greedy one, so very myopic heuristic, where we just assign every link some weight based on different attributes. And again, in this project, we used 3 combination topology, demand, traffic-based measures to assign that criticality measure. And then we rank them based on that. Then we use a k-shortest path, which is the second approach. And what we do there is for every link, we run the k-shortest path algorithm. Now, this is one of the most time-consuming out of the 3, because if you start going over 5, 10 paths, 10 k-shortest paths, it becomes very expensive to do so. So essentially, we figure out every link, where does it belong to, how many shortest paths, right? Because all the vehicles are going to go through the shortest path. So if a link, let's assume, belongs to all the shortest paths between an origin and destination, then that link is very critical, because if that link fails, the whole route from the origin to destination fails. So the network for that OD has been completely destroyed. And then we developed a random search heuristic where we assume that it's an intelligent attacker, and that's the one that uses the three-level problem: decision maker, attacker, and then the user equilibrium, the passengers, how they move, or the freight. And then we developed a custom heuristic how to solve it. Okay, so because there is no way to solve exact this problem, hierarchical problems are notoriously difficult to solve. So we did a heuristic where we go back and forth with some. We replaced essentially, if I can go into very briefly, we replaced the user equilibrium traffic assignment. We replaced it with an all or nothing, and then with a max min cost problem, just to replicate how the system is going to behave. So obviously, for people who are not interested in the research, those three algorithms that I described mean nothing, right? So what we did is we took them and we implemented them in ArcGIS. And the reason why we did that is so that anybody who wants to use these three algorithms and the framework that we created, they can do it as long as they have a roadway network and then a demand. So if you see here for the greedy search tool and for the random search heuristic tool, the one on the left and on the right, you need a network and then you need an origin destination matrix, which most MPOs will have, most DOTs will have, because they should have a travel demand model. So once you have those, then you can use, and I'm not going to go through how the tools work, they're going to be part of the report, and maybe we can have another webinar where we just present the tools and go through like a case study of how we use the tools, where they can actually run these tools and then figure out what are the links and the paths that are critical in their network. So now we're going to go a little bit into the case study and just showcase a few examples of the outputs. When we did the whole case study, we developed a geo database with all the results, because we did various different scenarios of capacity reduction between 20, 40, 60, 80, and 100%. So we're taking different scenarios based on if a link fails, by how much will it fail? Is it completely? Is it by a percentage? So obviously we cannot go through all the results here. I believe the report is going to be available within the next couple of months. We're just wrapping it up right now. So it's going to be available on the website along with the tools. So for this case study, the university in Florida, FAU, they were the ones who know the area more. Obviously, we're in Memphis. So we decided to go with Broward County, Florida, and they had the model, and we had the network and DOD, both for passengers and for freight. So that's the network that we used. You can see it here on the right-hand side of the PowerPoint. You see up on the left the bigger picture of Florida, and then zoom in where exactly the network is. So that's the network we used as a test bed for the model and the solution algorithms that we developed. So let's see some results and how it's going to look on ArcGIS, because again, ArcGIS is the software that we used, mainly because it's something that most MPOs and DOTs have. So there's not going to take any extra investment from the side of the public sector to use this tool. So over here, we're just ranking 10, 15, and 20 critical links. And obviously, as we start increasing those numbers, right, the whole network is going to become red. And then the previous slide was ranking links based on individual measures. And if you remember, we created 3 of them. And then you see how fewer are the links that are critical once you start combining those measures. So we had 3, and then individually with one of the measures. And then when we combine the 3 measures into one, you start seeing fewer links that become more critical. Now, I forgot to mention that there are certain links here that are not shown that are critical, and those are the links that if removed, the network is not going to be connected anymore between specific origins and destinations. So that's why you don't see those links here. So those links, we already know that they are critical. We don't need to have any model to tell us that. For example, if you look at Memphis, Tennessee, we have 2 bridges. I don't need a model to tell me that those 2 bridges are critical for my whole network. So whenever I'm doing an estimation of critical vulnerable links, I just throw them out. I don't care about them. I know they're critical. So I'm looking for the remainder of the links to figure out where they stand in the hierarchy. The other thing that the tool can do is give you a probability of attack that goes more into the area of if somebody wants to hurt a network. So it's not really focused on natural disasters or accidents, right? This is more if you have somebody who really wants to do something, a human being. And this can give you a probability of attack based on the assumption of how much the capacity can be reduced if somebody attacks the network. And then you get a probability for specific links, which are the ones that have a higher probability of being attacked. So you get different distributions, different histograms based on the different assumptions that you make in the model. And of course, one of the things that is more important, actually not more important, important for MPOs, for DOTs is paths, right? Because you want to pick a specific OD, especially if you're talking about freight, right? If I pick a port or if I pick a rail terminal and I want to see how much of that freight movement going from a rail terminal to a region or coming from outside of a state into the region to a specific terminal, a specific node, what are the paths that are going to be most vulnerable and where do I need to invest? This tool can do that for you. It can give you the paths. So here you just see the 10 most important paths for different origins destinations. And then that's pretty much in a summary the results that you can get, right? So essentially when you run the tool, you can get what are the vulnerable links, the critical links, the vulnerable critical paths, and then you can start playing around and looking into where you need to make your investments. Now, unlike any other project that I've worked on, this project is not something that you can put the results in a report. And the reason why you cannot do that is because you have so many results. And if you're, let me go back to one of the figures here, it's kind of difficult in a picture from a report to see what's going on. So the best way to look at the results is going into the ArcGIS and bringing up the maps that we created. And I think that's something unique about this project, that the report is almost never going to be used other than to look at the user manual for the GIS tool. And then everybody's going to just focus on the results in the ArcGIS environment. So when it comes to future research, this is just something that we saw that can happen. Obviously, there are tons of stuff that you can do when it comes to network design problems. And I've seen a lot of papers that have come up recently that take a different approach with regards to network resiliency. But something that we are looking into right now is different objective functions for the defender and the attacker, but that only has an application, again, if you're looking at a man-made attacks. So it really has nothing to do with, again, natural disasters. So it may not be of interest to MPOs or state DOTs. Then we're looking into multiple attackers with different objectives and multiple objectives for the decision maker. And things there get a little bit more complicated. The problems, at least so far, we have difficulty solving. We cannot come up with a solution. And then one item that we want to add is if a decision maker has a budget and they can fortify or increase capacity anywhere on the network, what would be the best decision to make in order for the network to be more resilient, right? To have a higher number of paths that have a reduced vulnerability. So that's something also that we're looking into, but then the whole approach needs to be modified because a budget and an investment decision needs to be included. And anybody who has done investment decisions for states and MPOs when it comes to the roadway network, they're quite complicated problems to solve. So those are the things that we're looking into. And I think I'm right on time with regards to our 20 minutes. And I think both Aline and I would like to thank you for your patience, and we'll be happy to take any questions, and hopefully we'll be able to answer them. And with that, I'll turn it over back to Vasya and Vangeli.
Thank you very much, Dr. Golia and Aline, for your presentation. Now, if you have any questions, you can either unmute yourself or you can type your questions in the chat and I will address them.
And Vasya, please call me Mike.
Okay.
If you can. Thank you.
I don't see any questions on the chat right now. You can either unmute yourself or you can type your questions in the chat.
Mihaly,
Okay,
Yes, I think there is a question with
Yes.
regards to calculating the risk of a link. So there are two things that we did. Let me go a little bit higher up. So we use different approaches to rank a link, right? And the one that's going to be chosen by the user depends on how much time they have and how big the network is. So when we're running our algorithms, the first thing that we do is my previous PhD student, Hannah Dakfiruze, she developed three combined measures, as we call them, right? That combine topology and then demand-based, like flow or travel time of a link. And then based on those, for every link in the network, we can calculate a risk. That's one way to do it. The other way to do it, which requires to run the random search heuristic, which then requires a traffic assignment, is we still use those risks, those calculated measures, as an initial risk. And then what we do, we go into an iterative process where instead of a user equilibrium, a shortest path or a max cost algorithm takes place. And that happens iteratively, like 1,000 iterations, imagine. And then we calculate essentially the risk of a link is the increase in the total travel time or the vehicle miles traveled, depending on which one we want to choose. And then that's assigned as the risk for a link. So depending if somebody has enough computational memory and time, would go with a random search heuristic because it's more accurate, because it looks into the actual travel time. But if somebody wants to run something quick, then they can use the weighted combination of the user-defined attributes, which are a combination of the topology of the link that has to deal with its centrality, and then how much flow that link is carrying.
Thank you, Mike. I would like also to mention that the presentation slides are going to be available on our website, along with the recorded video from the webinar.
Yeah, and the report for everybody, we're wrapping it up right now. So hopefully within the next couple of months, the report will have gone through the review process of FMRI, and the ArcGIS tool, the report, and the geodatabase that has been developed is going to be available to everybody because this is a federal sponsored project, so everything is available for everybody. Excluding I'm not sure. What is the estimated time and effort to put this into an MPO resilience process? The tool can be used as is, Matt. The added process would be that the MPO will need to have its own travel demand model. If it doesn't, then we can borrow from the statewide model, but obviously the accuracy rate is going to be less because usually statewide models don't have they don't have such an accurate network when it comes down to a city or an MPO level. And then just run the GIS tools, which can be done, I mean, after a couple of hours of training, or even no training. If somebody's familiar with ArcGIS, they can look at the user manual that's going to be available. We have another question that says, if we identified key threat countries. No, we did not look into that area, Gail. We are not making any mention with regards to threats from a national security perspective. We're just saying that this tool, if there is an intelligent attacker who knows a few things about traffic and traffic assignment and can get an idea about traffic flows of a network, which again, this can be a very big discussion as to what the attacker may know about our network here in the United States, then that model can take into account that, you know, they're not blind, they can actually see, and then when they're making the decision to attack somewhere, they're going to consider that. And the model takes that into consideration and then tries to fortify the best links. So it minimizes the final effect to the users.
Thank you, Mike. I don't see any other questions in the chat right now.
Well, and I do think that our information is available. So maybe, you know, I usually get some emails afterwards when people really go, you know, they look into the report. Because at least from my case, whenever I see presentations, it's kind of difficult to digest everything at that 20 minutes. So usually then when I read a paper or a report, I get a better understanding and then I have more questions. So Vageli, Vasily, correct me if I'm wrong, our emails are going to be shared with everybody. So please, any question you guys have, shoot us an email. We love to do that because we're researchers, so we love to interact. And a lot of times from the questions come actually research ideas. You know, did you do this? And you're like, oh, that's a good question. Maybe we should.
Mike, this work has been submitted to the TRB.
Part of this work has actually been published in the TRR. But and I don't remember. I think we submitted. Yes, I think we submitted 2 more papers for this TRB, but it's still under review.
Excellent. If they need, we can distribute. Also, I will ask you to forward to Vasya the published papers from this work, so we can circulate between the DOT people.
Yes,
here
of
in
course,
Florida.
of course. If you don't mind, Vageli, we can wait for the other 2 papers. But once we get the reviews back, we can send them as drafts as well.
Sounds good. Let's wait, and when we have the green signal from you, we can distribute among the DOT people, because they ask me if we have published anything from this work.
Well, 1 paper has been published in the TRR, obviously presented at TRB, right? Because in order to be in the TRR, you have to go through the TRB first. And then we have 2 papers submitted to the TRB. Now, if either of them or both of them don't get published in the TRR, they're going to be submitted to a journal after we incorporate any comments from the reviewers.
Sounds good. Thank you. Did you see, Mike, did you see a possibility to extend this work for another year down here in Florida, or to include this model in more than one state? What do you think?
Well, the good thing about the way it's built now, right, because it's automated, it's a tool you can apply to other states as long as you have a network and an OD, right? Because you need those basic things. Now, the thing that is really missing from this is the investment part, because we haven't included anything with regards to investment, because at the end of the day, you don't really care about the results from this model. What you care about is to go and say, you know what, I-40 between milepost X and Z, we need to increase capacity, or we need to fortify, or we need to do this, we need to do that. Or if you're looking at evacuation routes that you have, are those vulnerable? Are those critical? Although most evacuations have been picked in such a way. But usually my understanding is those are picked based on flow and capacity. So obviously, as a researcher, we mentioned tons of stuff that can be done, but I think the most helpful one would be including, if I have a budget, where do I spend it in order to maximize my return on the investment?
Thank you, Mike. Sounds good to me. Do you have any other question, Vasya?
No, I don't see any other questions in the chat.
If we don't have any other question, we would like to thank everyone that attend this webinar. And Vasya, could you please let us know when is going to be the next webinar, and what is the topic about?
Yeah, sure. First of all, thank you very much, Mike and Aline, for your presentation today. Our next webinar is on September 16th with Aline Machado. which she's going to talk about the critical freight corridors. Again, thank you everyone for attending this webinar, and we are looking forward to see you again in the next one. Thank you very much. Thank you, Mike and Aline, again.
And I would like to thank Aline because for her patience and for her hard work on this, because we worked very closely on this one, and I kept bugging her with emails back and forth, and we couldn't have done it without her. So Aline, thank you so much. I really appreciate all your help and efforts on this.
Thank you.